Deep down in the oceans, sometimes several kilometers below the surface, you can occasionally come across formations that seem to come straight out of another world. On lakes that have formed beneath the seas, and on strange ice mounds, and even on mud volcanoes. Located between 3,000 and 6,000 meters deep, the abyssal plains are among the least explored regions on the planet. At first glance, these vast expanses, which alone cover more than 50% of the Earth's surface, are strikingly monotonous. By moving around here, you are, in a way, flying over the largest desert in the world. Almost everywhere, as far as the eye can see, the landscape before you is that of a flat plain without any relief or contrast. A uniform plain, covered by a thick layer of sediments made up of fine particles of organic matter, which, coming from the surface, continually feed the ocean floor in the form of marine snow, with deposits accumulating at an average rate of 1 centimeter every 1,000 years. But in this desolate monotony, only disturbed by the few living creatures that inhabit it, it occasionally happens that, piercing the darkness, the beams of the submersible's spotlights illuminate strange formations. Solitary structures that seem to emerge here and there from this desert beneath the seas. You are not facing a mirror, but a miniature lake lying at the bottom of the ocean, whose surface separates two liquid worlds that no longer mix. Known since the mid-1960s, these unreal-looking pools are brine lakes that form as a result of the accumulation of extremely salty water. This water can contain 5 to 8 times more salt than seawater, and, being much denser than its surroundings, seems to settle in basins whose surface forms a shimmering boundary between them and the rest of the ocean. Only a few dozen meters deep at most, many of these formations have been recorded, their size so modest that they resemble puddles just a few meters in diameter. But the largest ones that have been discovered cover 60 square kilometers. Sometimes, these kinds of miniature dead seas lying in the depths of the abyss even seem to be covered with strange layers of mist, because thanks to the currents, a zone can form above them where the waters manage to mix slightly. So these mists conceal salt-saturated lakes beneath them, on which exploration submersibles sometimes bounce when they try to break through the surface. Some autonomous underwater robots that ventured too deep into these brine pools almost got trapped there. The water there is so dense they almost got stuck. Although it is estimated that several hundred of these spectacular underwater lakes currently lie between 700 and 3,000 meters deep at the bottom of the oceans, we have so far identified only about 50 of them. Most of them are in the Gulf of Mexico, the Red Sea, and the Mediterranean, where, in the depths of the Aegean Sea, 3 kilometers below the surface, about 10 brine pools have been discovered, and you can see their locations on this map. Almost all brine pools are formed above ancient salt deposits that were created millions of years ago, when ancient seas, after being closed off, evaporated, leaving behind the salt they contained, and which was buried and covered by sediments over time. When seawater in the depths of the ocean seeps through cracks, it can reach these thick layers of salt, sometimes several kilometers thick, and leach them before slowly rising back up through the crust. Then, it flows further onto the ocean floor, giving rise to ephemeral rivers that eventually form these strange natural pools. For most organisms that have also ventured into these lakes, they are death traps because the composition of this water that seeps from the Earth's crust is truly poisonous. Because of their hypersalinity and the inability of currents to mix them with the ocean, these waters contain virtually no oxygen molecules. Anoxic, they are deadly for all organisms that breathe. So, when an animal enters a brine pool, it suffers toxic shock. As a result, these places are often littered with the corpses of fish, crabs, and amphipods that ventured too far into these tombs of the deep. Once dead, all these organisms are strangely preserved in the hypersaline liquid for decades, because the toxic nature of these pools prevents the microorganisms responsible for decay from developing there. And certain minerals, such as barium sulfates, even wrap the bodies in a thin crystallized layer that turns the dead into statues. So the edges inside these pools are often cemeteries of bodies, frozen and extraordinarily well preserved at the bottom of the seas. In the Gulf of Mexico, the famous brine pool, known as the Jacuzzi of Despair, is littered with dead animals that have been suffocated by these waters in which they cannot breathe, or poisoned by the high concentrations of methane, sulfuric acid, and dissolved hydrogen sulfide found there. Yet, although these pools are deadly traps for most living things, life has invented new strategies to exist there. In fact, on the shores of these poisoned pools in the abyss, there are organisms that have managed to take advantage of these extreme conditions. On the outskirts of these pools, colonies of bacteria thrive, having developed an ingenious process called chemosynthesis, which allows them to produce energy from the toxic substances found there, without relying on the fine organic particles that come from the surface. And as a result, the existence of these bacteria allows a whole variety of unusual and diverse fauna to survive and thrive on the edges of these deadly pools. Indeed, here we find ourselves in a narrow range between the brink of death and the realm of life. Beds of giant mussels thrive here, hosting these bacteria in their gills, which transform and convert toxic elements into digestible food for them. So the edges of these pockets of poisoned water are paradoxically oases of a new kind of life, flourishing in the midst of almost barren abyssal plains. Because, unlike the realm plunged into eternal night that surrounds them, where animals can only rely on scraps of food drifting down from the surface to feed themselves, here there is a primary source of organic matter, continually renewed by the proliferation of bacterial mats. Beyond the strange creatures that live there, we can observe deposits around these pools formed by the activity of living beings. By studying the size of these carbonate reefs that develop and accumulate over time, the age of some pools has been estimated at around 15,000 years. Although they have often existed for several millennia, these islands of abundance are not eternal because the fractures through which the toxic water that feeds them rises can close up and the infiltration can stop. Deprived of their energy sources, the extremophile microbial mats eventually disappear, and with them, all the organisms that depend on them. And just to add another layer of weirdness to the strange, consider that in all the oceans of the world, at depths ranging from a few hundred to several thousand meters, you can find them. Areas where the seafloor seeps an invisible sap in the form of bubbles of methane, hydrogen sulfide, carbon dioxide, and sometimes even heavy hydrocarbons, either liquid or viscous. At these strange formations called cold seeps, which were first discovered in 1983, water rich in toxic chemical elements flows from the Earth's crust at temperatures between 2 and 10 degrees. Often much larger than the brine pools with which they are frequently associated. These formations do not originate from the dissolution of salt, but from the upwelling of fluids rich in hydrocarbons. They too find pathways through faults and fractures to escape from the deep sediments and eventually reach the ocean floor. Here too, the chemical content of these fluids, which come from the slow breakdown of buried organic matter cooked deep underground, is a valuable fuel for another kind of life. At these seepage sites, the ocean floor is covered with massive specialized microbial mats that know how to transform hydrogen sulfide or methane into precious vital energy. In some places, these mats, which look like mold in white, yellow, and sometimes even bluish colors, literally cover the underwater landscape as far as the eye can see. Because the largest of these seepage sites cover an area equivalent to that of the city of Paris. We also find here many animals that benefit from the existence of these extraordinary microorganisms, which are able to produce their energy without any connection to the surface, such as giant mussels that host them in their tissues. or even tube worms, which, lacking a mouth, anus, and intestine, owe their survival to the symbiotic relationships they maintain with their chemosynthetic bacterial flora, which indirectly provides them with the nutrients they need. Able to burrow into the sediments and absorb sulfide through their roots, these worms often gather in clusters that can contain several hundred individuals. With slow growth, they can reach truly prodigious sizes and lifespans. The largest ones ever found are nearly 3 meters long, and their age has been estimated at around 400 years. At these seepage sites, huge colonies of yeti crabs sometimes also flourish, hosting chemosynthetic bacteria in the long hairs that cover them, which they wave in the sulfur-rich water to help the bacteria grow and benefit from them. The presence of all these animals also attracts a myriad of others that depend on them for food, such as anemones, shrimp, copepods, snails, and deep-sea fish. As a result, you can find several dozen kilograms of organic matter per square meter here. And all these creatures, living under pressures equivalent to those exerted by a semi-truck placed on the surface of a hand, are only a few kilometers away from where we live. Because almost all regions rich in cold seeps, whose distribution of the largest known sites across the planet you can see on this map, are located near the coasts, along continental margins or oceanic trenches, where tectonic activity forces deep hydrocarbon pockets to release part of their contents in the form of more or less viscous fluids or gas. Although the number of seeps worldwide is difficult to estimate, it is believed that there could be several tens of thousands, of which less than 5% have been located. Along the east coast of the United States alone, more than 550 active sites have been identified over just a few hundred kilometers. The abundant life that develops here even plays a major role in regulating the global climate. It is believed that between 50 and 90% of the methane escaping from the seabed at these toxic pockets is consumed by the activity of microbial organisms before it enters the water column. Just like the brine pools, the location of these seeps changes and shifts over time. The oldest ones that have been found have existed in the same place for nearly 50,000 years. Sometimes in these oases of life, you can even come across mounds that look like ice or compacted snow. A snow that is nothing more than methane hydrate, kept solid by the freezing temperatures and the pressure of the water column. These curious formations, inside which methane is embedded and trapped in a cage of frozen water molecules, are regularly colonized by life forms capable of ingesting and transforming chemical elements into usable resources. Normally, these hydrates are stabilized by the pressure and cold that prevail on the ocean floor. But when an imbalance occurs, the microscopic crystalline cages that keep the methane trapped can give way. And the trapped bubbles then escape from their frozen matrix, creating surreal scenes like these blocks of hydrate captured as they rise above the ocean floor and ascend through the water column as the bubbles inside them are released. Sometimes, these bubbles even attract deep-sea animals, as shown in these images taken by a rover from the Mbari Institute, where you can see a crab trying to catch them, probably mistaking them for food. As harmless as they may seem, all the methane hydrates currently present between 200 and 2,000 meters deep in all the world's oceans contain the seeds of a small apocalypse. In the stability of these cloudy methane ice grains, a part of our climate future is at stake. Because on a planetary scale, the amount of methane currently trapped in this deep-sea snow is absolutely phenomenal. All the methane found there combined has a greater potential to warm the atmosphere than the combustion of all known reserves of coal, gas, and oil put together. So their sudden release would trigger a colossal climate crisis. In fact, it's believed that this has probably already happened in the past. About 56 million years ago, during the Paleocene-Eocene thermal maximum, the average temperature of the planet rose by nearly 5 to 8 degrees in just a few millennia. Although the origin of this sudden warming is not yet well understood, carbon isotopes found in sediment cores from that time indicate a sudden and massive release of light carbon into the atmosphere. A type of carbon identical to the one found in methane hydrates. It is believed that at that time, intense volcanism combined with the movement of the continents could have warmed the shallow marine sediments and triggered the release of hydrates and the massive release of methane into the ocean and then into the atmosphere. The warming from this would in turn have amplified the rise in temperature of the ocean floor, creating a hellish cycle of self-reinforcing feedback loops. Today, the temperature of deep waters is slowly rising, and some observations raise concerns that one day, this warming could awaken the thermal bomb lying dormant in the silence of these sediments on the ocean floor. Less photogenic, but perhaps just as strange as the hydrates, several thousand cold mud volcanoes have been discovered under the seas. Huge mounds that don't spew lava, but release thick clays in a misty and oppressive atmosphere. These underwater mud volcanoes, whose heavy eruptions spit out sediments, are formed by the rise of pressurized gas that escapes from deep within the soft parts of the Earth's crust, where it has been trapped for millions of years. As it rises quickly through the fractures, this gas tears away some of the material, making up the soft sediments it passes through, forming at the exit a dome that can reach extraordinary proportions. Some eruptions observed by sonar form columns of cold mud several hundred meters high and can release thousands of cubic meters of sediments in just a few hours. Around these structures, which can exceed 200 meters in height and reach several kilometers in diameter, the ground, rich in clay and organic matter, is highly unstable. Around the Akon Mosby mud volcano, located off the coast of Norway, spectacular microbial fields have developed, along with a unique fauna that has managed to adapt and thrive in these muddy, methane-rich sediments. Although the activity of these mud volcanoes is only marginally affected by surface warming, their contribution to natural methane emissions is of the same order of magnitude as those coming from the melting of hydrates. And it is believed that they too have contributed in the past to amplifying global temperature variations. Finally, more anecdotal but just as strange, in 2014 a submersible came across, at a depth of 1,900 meters in the Gulf of Mexico, a huge structure that looked like frozen flowers made of tar et de bitume lourd. It is believed that this astonishing structure was formed by viscous oil which, after rising from the deep reservoirs it comes from, stopped flowing and quickly solidified upon contact with the cold water, taking the shape of petals. Petals on which a large number of bacteria were found, capable of transforming the tar into assimilable matter and thriving on heavy hydrocarbons. Beyond their striking beauty, which in itself is already a reason to study them, all these unique ecosystems are laboratories. Because the organisms that live there have often developed biochemical processes unknown to surface-dwelling living beings. So there is a whole pharmacopoeia just waiting to be understood and deciphered. Consider that today, nearly 50% of cancer treatments are derived from molecules found in marine organisms, some of which live in these brine pools. The venoms of many deep-sea mollusks are currently being studied to create painkillers that are 1,000 times more powerful, volume for volume, than morphine. And studying the hemoglobin of tube worms could one day make it possible to create artificial blood and a universal donor type. As for the bacteria capable of breaking down heavy bitumen, they may one day revolutionize the chemistry of soil decontamination. And beyond these practical applications, the existence of all these extreme ecosystems reminds us just how remarkably life is able to thrive. Where forms of life are able to proliferate without light or oxygen and to thrive on elements that are so toxic, they would make you instantly regret being born if you were unfortunate enough to ingest them. This has also profoundly shaken our way of thinking about life elsewhere in the universe. Today, these environments fascinate astrobiologists who study them closely. Because here, reproduced on a small scale, are conditions similar to those suspected to exist on other worlds. Cold seeps, as well as hydrothermal vents, which I haven't talked about in this episode and to which we've already devoted half an hour because they deserve it, are lessons in resilience and molecular tenacity. Places where biology invents new rules in the shadow of the main principles mostly used on the surface. If life is able to thrive thousands of meters deep in total darkness, and by relying on compounds that are highly toxic to almost all other living species, then nothing really stops us from considering it plausible that it could exist elsewhere on other planets. From there, imagining the presence in the depths of the oceans buried under the ice of the small moon Europa, or in the seas of liquid methane on Titan, of islands of adaptation of a similar kind, is just one step that I am terribly eager to take.